Explain what is meant by a field of force. Field of force. These are like field of force. In general terms, it means where you experience of force. Where since it's Cambridge, you know, they got issues. So you just write regional space. You write in their terms regional space where a particle will experience force. Right. State the type of fields that will rise to a force acting on. Now this is a very interesting part. So far in Cambridge we will learn about four fields: gravitational fields, gravitational, electrical, magnetic. Let's write out the equations. For the gravitational fields, we know the gravitational field strength depends on the gravitational constant, mass, and the distance between the objects or masses. The electrical force, on the other hand, depends on the electrical field strength depends on the force per unit charge, and the magnetic field depends, or they can say the force of the magnetic force depends BQV sine theta or BIL sine theta. For a wire, it depends on the current. For a particle, it depends on the charge and the average drift velocity. Now let's come to deductions. We'll write GEM, GEM, GEM. State the type of fields that will give rise to a force acting on a moving uncharged particle. On a moving uncharged particle. When you're talking about uncharged particle, we are already crossing out the options electric and magnetic. So you're only left with gravitational, because gravity, that goes with everything. It's your everyday neighbor. Then a stationary charged particle. We have a stationary charged. When talking about charged, we have two possible candidates: electric field or magnetic field. They both have a charge in this equation. But now in magnetic it needs to be moving, otherwise we won't experience any force. So we can cross out the magnetic. So it will be electric and gravitational. Yes, like gravitational force or gravitational field is like, you know, gravitational and electrical. Now charged particle moving at an angle to the field or fields. Alright, moving a charged particle will still experience the gravity as long as the gravitational force. As long as they have mass, they will face this. And since they're moving at an angle, it's magnetic. Regardless of the charged particles, it obviously feel electric force. Next question. An electron, right? Mass m, charge q, negative q, is moving at a speed v in a vacuum. It enters a region of uniform magnetic flux density b. So let's say the path of the electron goes like this. It then bends. Alright. Initially the electron is moving at right angles to the direction of the magnetic field. We can see that. Let's try to understand first whether the field is into the page or outside the page. Since the negative particle is going this way, so the conventional current will be in this way, and it is bending in this direction. So let's say for here the force will be acting in this direction. Right, using the Fleming's left hand law, imagine it's on a table. Your middle finger goes towards you, the force is towards the right, and the first finger goes into the plane. So yeah, so it goes into the plane of the paper. The field is, sorry my bad, field is into the plane of paper. It will just make life easier. Initially the electron is moving at angles. So explain why the path of the electron in the magnetic field is the arc of a circle in a circular system, right? In a basic knowledge, we know in a circular motion we have our direction of motion is a constant. It is due to, and we have a centripetal force that is acting towards the center of the circle. They are perpendicular to each other. Right, now let's coming back to the answer. We are seeing, so we'll just state the points from the circular arc, just make life easier. Why do we need to waste it over here? Because they have difficult parts to counter in exam. We'll just write force is always normal to direction of motion, and we'll write the magnetic field. The magnetic force provides the centripetal force, and as you can see, magnetic force is constant. So is the velocity. Hence, it's an arc.